Hi, welcome to my first IDLI live session. Today I will talk about reinforcement learning and how it aims to achieve our dream of artificial general intelligence. My name is Anirban Santara. I am a Google India PhD fellow at Indian Institute of Technology, Kharagpur. I graduated from the same institute in 2015 with a BTech degree in electronics and electrical communication engineering. I've been working in the field of deep learning for the last 3 years. The contents of this session are as follows. First, I will describe the reinforcement learning problem statement and formalize it mathematically. Next, I will present some algorithms for learning policies in an RL setting. I will wrap up the session with highlights of some recent breakthroughs in this area. The duration of this session is 1 hour. Please feel free to post your comments and questions in the comment box. I will answer them in between subsections of my presentation. Refers to learning through trial and error, using feedback from the environment. There are two main entities, the environment and the agent. The environment manifests itself in the form of different states. The agent observes the state of the environment and takes actions. Depending upon the action of the agent, the environment changes its state and provides the agent with a feedback signal that is qualitative of the agent's performance. This feedback signal is called return or reward. Let us illustrate with an example. What you can see on the screen is the video of an RL agent trying to drive a racing car in the Open Racing Car Simulator, or TORCS talks. Time, the agent receives information about the current state in the form of a set of state variables, like its position in the track, its distances from the track edges along different directions, its direction of heading, and its current speed. The values of the state variables, the agent has to choose its action. Will comprise of values for the action variables like steering angle, acceleration, and brake. Depending on the agent's action, the state of the environment will change, and the agent will be provided with a new set of values for the state variables at the next time step. The agent has to drive around the racing track in the shortest possible time, avoiding collisions with obstacles. Now say we wished to solve this problem using supervised learning. For that, first, we would have to create a training set with examples of the form xi, yi, where xi are the states of the environment and yi are correct values of actions in those states. Now, finding correct values of actions is often hard. Nevertheless, if we have a training set, we can fit a regression model to predict actions given states. An unsupervised learning algorithm would, on the other hand, take absolutely no information about the correctness of the agent's actions. A reinforcement learning algorithm would use the reward signals from the environment as feedback about the agent's performance. The reward signal in this case can be a +1 for every time step the agent manages to stay on the road, -1 if it comes to a halt, if it bumps into an obstacle, and +100, a huge positive reward, if it finishes the race. Signals are often sparse and delayed. Reinforcement learning algorithms use various techniques to address these issues. Reinforcement learning problems are often specified in terms of a Markov Decision Process, or MDP. An MDP is a tuple. It consists of the following: a set of possible states S, a set of possible actions A, a transition probability function T that gives the probability of the next state given the current state and action, a reward function R that returns a real number for every state action pair, the initial state distribution, rho 0, and a temporal discount factor gamma that we will talk about in a bit. The word Markov in Markov decision process stands for the Markov assumption in the definition of the transition function T, which says that given the current state and current action, the next state is conditionally independent of all previous states and actions. A policy is a function that predicts an action for a given state. A trajectory is a sequence of state action reward tuples which represents an episode of interaction between the agent and the environment. For example, in the case of the agent driving a racing car, one lap around the racing track may represent a trajectory. The reward of a trajectory is defined as some function of all the reward signals received by the agent in the trajectory. For example, it can be the sum of all the rewards. Another popular choice is the discounted sum of rewards with temporal discount factor gamma, which we talked about in the last slide, which is defined as an element of the MDP. The goal of a reinforcement learning algorithm is to find a policy pi star that maximizes the expected value of trajectory rewards. I will introduce you to some algorithms for policy learning. An important concept crucial for learning effective policies is known as the exploration-exploitation dilemma. At any particular point of time during training, the agent can either act according to whatever policy it has learned till now, or so this thing is referred to as exploitation. Or it can try some random actions and check if there is a better alternative to this learned policy. This is called exploration. The interesting fact is that if the agent decides to exploit right from the start and keeps exploiting forever, it remains stuck with its initial policy and never learns a thing. On the other hand, if it decides to explore all its life, then it keeps choosing random actions and ends up learning no effective policy. Finding the right trade-off between exploration and exploitation is effective policy learning. The first algorithm that we will study for learning policies is called policy gradient algorithm. Policy gradient algorithms directly learn a model of the policy by calculating the gradient of the expected reward function with respect to the policy. It's a parameterized model of the policy network. The parameters of the model are learned by gradient ascent on the expected reward function. The pseudocode for policy gradient algorithm can be written as follows. First, we initialize the policy pi theta with theta equal to theta 0 and set time t equal to 0. Next, we generate n trajectories tau I equal to 1 through n, by acting randomly with probability epsilon, that is exploration, and by acting according to policy pi theta t with probability 1 minus epsilon, that is exploitation. Now we calculate the trajectory rewards for each of the n trajectories that we generated in the last step and calculate the expectation of the reward. Next, we calculate the gradient of this expected trajectory reward with respect to the policy parameters and take a gradient ascent step on the policy on the policy parameters using a learning rate eta. And then we keep on repeating until we have achieved convergence. If you have any questions, please feel free to use the comment section. I will reply them. The next family of algorithms that I will talk about is called value function based algorithms. There are two popular value functions. The state value function, or V pi s, is defined as the expected future reward obtained by starting at state S and acting according to policy pi. The state action value function, Q pi SA, is defined as the expected future reward obtained by taking action A in state S and thereafter acting according to policy pi. The optimum value function is defined as the maximum value of these value functions maximized over policy pi. The definition of the optimum state action value function, or Q function, leads us to the following interesting equations, known as the Bellman equations. The first identity gives us a recursive definition of the optimum Q function. Given the optimum Q function, Q star SA, the optimum policy can be evaluated simply by greedily choosing the action that maximizes Q star at every state ST. This is also known as Bellman optimality condition. Value iteration algorithms like Q-learning use the Bellman equation B1 to estimate the optimum value state action value function iteratively. It can be shown that as I tends to infinity, Qi tends to the optimum value function Q star. When the state and action spaces are discrete or finite, then QISA can be represented as a table of size, number of states, cross number of actions. This table can be updated iteratively using the first Bellman equation. The pseudocode goes as follows. First, you initialize the Q table. And these initial values can be random. Let us call it Q0SA. Then we sample n trajectories, tau I equal to 1 through n, by randomly acting with probability epsilon. That is, we explore with probability epsilon. And rest of the time, we use a policy, which is this formula, that is argmax over all actions of QISA. That is, we greedily follow the Q function that we have learned till now. Then we update the Q table using the Bellman equation for the state action reward next state pairs, like tuples, taken from the trajectories that we had sampled. We repeat these steps until the value of Q function converges. And at convergence, the values are the values of the optimal Q function, that is Q star. Once we have Q star, we can find the optimal policy by acting greedily according to the Q function. When the state and action spaces are not discrete or finite, QISA can no longer be represented as a table. Hence, function approximation is used. This family of algorithms represents QISA as a function Q theta, where theta is the set of parameters that have to be learned. Theta is learned by gradient descent on the error function, which is defined as follows, where eta is the learning rate. The famous deep Q network algorithm uses a neural network as a function approximator, along with some hacks like experience replay to make the samples IID. Let us look at some pros and cons of both the classes of algorithms. Policy gradient algorithms tend to work well in conjunction with function approximation and continuous features. They also scale very well in large state action spaces. The disadvantage is that usually only the local optima and not the global optima can be found. Value iteration algorithms, on the other hand, have the advantage that if the complete optimal value function, that is the optimal Q function, for example, is known, then the optimal policy can be followed simply by greedily choosing actions to optimize the optimal value function. The disadvantages of value iteration algorithms are that if total coverage of state action space it's not available, then the methods become extremely brittle. Also, these methods are unstable under function approximation in high dimensional continuous state and action spaces. Hence, in such situations, policy gradient algorithms are a better choice. The next category of algorithms that we will look at are called actor-critic algorithms. Policy gradient algorithms are called actor-only algorithms because they directly try to reduce the optimal policy. Value iteration algorithms, on the other hand, are called critic-only algorithms because they first observe and estimate the performance of choosing controls on the system through the value function and then derive a policy out of it. Actor-critic algorithms incorporate the advantages of each of the above. They have a policy gradient component called the actor, which calculates policy gradients. They also have a value function component called the critic that observes the performance of the actor and decides when the policy needs to be updated and which action should be preferred. Next, we will look at some recent breakthroughs in the field of reinforcement learning. In 2015, Google DeepMind's novel network agent beat all previous algorithms and achieved human-level performance in the challenging domain of Atari 2600 games. In 2016, DeepMind's AlphaGo defeated one of the world champions at the ancient Chinese board game of Go, which is considered many times tougher than chess. A few months back, Elon Musk founded OpenAI's robots learn to develop their own language to interact in a common world. The world of reinforcement learning is huge. I am young in this area, just 3 months old, and I find it utterly fascinating. I will leave links to resources for further reading in the description of the video. Thank you so much for watching. I would like to thank the Indian Deep Learning Initiative, or IDLI, for organizing this talk, and Dr. Jacob Mins to actually bear all the hard work of moderating this talk and also managing this live video session. Thank you very much. I loved it. This was the first ever YouTube live video session I have done in my life. Have a good day. Bye.